Hey there, how you doing? Let's enter into a new chapter, promising one. So far, we have been solving physics problems by applying Newton's second law, F equal ma. We do this because our old friend Isaac Newton realized that when acted upon by a force, one object of mass m accelerates with acceleration a. This is an experimental approach to understanding nature. And we feel very comfortable with it because it is based on observation and experimentation. It makes sense. It is intuitive and it agrees with our daily experiences. But nature does not need to do any of this. It does not need to be intuitive and related to our daily experiences. As examples, we have quantum mechanics and relativity. Another way to approach classical mechanics is through a new concept called the action, and the principle that makes this action an extreme. This principle of stationary action that we'll talk about in this chapter leads to some equations that happen to coincide with Newton's second law. Mathematically, they give the same result, but physically, they are telling us something more about nature. Nature has some preferred way of behaving, and in that way of life, nature likes to minimize and sometimes maximize this action. To get started with this approach, I will present a couple of examples, and in coming videos, I will introduce what action is. From a mathematical point of view, we can define new functions at will, right? So, allow me to introduce a function L as the kinetic energy of the system minus the potential energy of the system. So, L equal K minus U. Let me call this function the Lagrangian after the Italian mathematician from the 18th century. Be careful that there is a negative sign there, so it is not the energy of the system, it's something else, something different. Let's, for example, write this for our old frame and mass on a spring. The kinetic energy is 1/2 of mx dot x squared, and the potential energy is 1/2 of kx squared. So the Lagrangian writes as this. Now let me take from my magician hat this equation in derivatives, which I will call Euler-Lagrange equation. Yes, I know this is a course on physics, not on magic. Just stay with me and I will explain this equation later. Let's apply this equation to the Lagrangian of the mass and the spring. The partial of L with respect to x dot is mx dot, then its derivative with respect to time is mx two dots. The partial of L with respect to x is negative kx. Let's substitute this here and we get Newton's second law. How curious, isn't it? Okay, let me study something a bit more general. Let's consider a particle under an arbitrary potential u of x. The Lagrangian for that particle is if we apply Euler-Lagrange equations, we get that mx two dots is the negative derivative of the potential energy with respect to the position. Well, this we already knew, because this negative derivative is nothing else than the force related to the potential. So this is again F equal ma. We'll see one more example in the next video and then show where those equations come from. Meanwhile, may the science be with you.